Hi everyone. Today's video is about Section 4.1, which is an introduction to polynomials. Last time we were together, we did quite a bit of talking about polynomials, but we never really decided what a polynomial is. To form a polynomial, we start with a ring, R, and then we have this additional object, x, that we call an indeterminate. And that x is not in R. Then to form a polynomial, what we do essentially is take a finite linear combination of whole number powers of x, where the weights on this combination, the a0, a1, through an, are members of our ring R. Those are called coefficients. Now, we can just think of these powers of x for the moment as being placeholders. And the plus signs in this expression we can just simply view as separating these placeholders. Now, if the a sub n is a non-zero element in our ring, then we call that a sub n the leading coefficient. And we let n, this sort of largest power of x that's associated with a non-zero coefficient, we let that n denote the degree. So every polynomial has a degree, either 0 or 1 or 2, etc., except for the zero polynomial. So we do not allow the zero polynomial to have a degree. Now we denote the collection of all of these polynomials by r with an x in square braces next to it. So this notation here denotes, so that's the collection of all polynomials with coefficients in R. And if someone hands you two polynomials and asks you whether they're the same, the way that you do it to check is you just compare coefficients. If the coefficients are identical, then the polynomials are the same. If they are not, then the polynomials are different. Now, even with all of this, what I've told you about the definition of polynomials is not a complete story. There's a formal definition of polynomials that's given in Appendix G of our textbook. And if you're interested, you can look back there and see all about that. Lately, we've been doing a lot of talking about rings, and this collection of polynomials with coefficients in the ring R is itself a ring under the following operations. So if I have two polynomials, say a0 plus a1x up through an x to the n, and I want to add that to b0 plus b1x up through bn x to the n, essentially what we do is we're going to just add together coefficients of like powers of x. So for instance, in my new polynomial that's supposed to be the sum of these two original polynomials, if I want the constant term, what I do is just add together the constant terms of the original polynomials. And then if I want the coefficient for x, I simply add together the coefficients of x in the original two polynomials, and so on and so forth until I get to the last term, which is x to the n. If I want that coefficient, I just simply add together the coefficients of x to the n in the original two polynomials. Now, it might look here like we are only able to add together polynomials that have the same degree, but that's really not the case here. We have not declared that both an and bn need to be non-zero. Essentially what we're doing here is we're letting n be large enough to pick out all of the non-zero coefficients of this polynomial and all of the non-zero coefficients of that polynomial. Okay, now moving on to multiplication, we have a formula here for multiplying two polynomials. We get a new polynomial with coefficients c0, c1 up through c sub m plus n. And then we have this rather disconcerting formula for the kth coefficient c sub k. And I want to assure you that this formula is no different from what you ordinarily do when you multiply polynomials. What you're doing is you're just gathering together all of the coefficients from the like powers of x. So here this is, you get all these middle terms, and you're going to get a lot of, say, x to the k's. And these are the sum of all of the coefficients of those x to the k's that occur. Now here, what we need to be very careful, though, about one thing, and that is that the ring R that we start with might not be commutative. And so the order that we multiply the a's by the b's, that is very important if R fails to be commutative. So you'll need to keep that in mind. However, in most of our applications, R is going to be commutative, and we won't have to worry about that very much. Okay, so a few things to note. First of all, you can view the ring R as a subring of the collection of polynomials. In fact, if you look at just the collection of constant polynomials, that is, those of degree 0, those are a subring of the collection of polynomials that's isomorphic to the ring R. Now, if R happens to have an identity, then so does the ring of polynomials, namely the constant polynomial 1 sub R works as a multiplicative identity. And if R is commutative, then so is the ring of polynomials. In particular, this formula for coefficients in the product, that will turn out to be the same whether the A's come first or the B's come first, if the underlying ring R is commutative. Okay, we illustrate these operations in the polynomial ring Z5 adjoin X. Here, so this is just polynomials with coefficients in Z5. Now we have these two polynomials f and g that you can see here, and we're going to add them together and multiply them. So in adding, we just want to add together coefficients of like powers of x. And here we have only one, among these two polynomials, there's only one that has a constant term 2. So I just grab that and write it down. And then I look at x to the 5th, and I see that I have 3x to the 5th and 4x to the 5th. So in the new polynomial, I'll take 3 plus 4 as my coefficient of x to the 5th. And then for x to the 6th, we have 1x to the 6th represented in g, and 0 of them in f. So we just get one of them overall. And then we remember that we're working over Z5, and 3 plus 4 is equal to 2 in Z5. So this is just 2 plus 2x to the 5th plus x to the 6th. And that's the sum of those two polynomials. Now, multiplying them together, we do this just as we would ordinarily, but we have to remember that we're working over Z5 and not over some other ring. Right? So I multiply these two together, and the first thing that I might do is take 3x to the 5th times x to the 6th. That would give me 3x to the 11th. Then I might take 3x to the 5th times 4x to the 5th, and that would give me 12x to the 10th. And then I take maybe 2 times x to the 6th, which gives me, guess what, 2x to the 6th. And then I have 2 times 4x to the 5th, so that would be 8x to the 5th. But now we remember that our coefficient ring is Z5, and so we want to make sure that we write all of these coefficients in Z5. So this would be 2x to the 10th instead of 12x to the 10th. And instead of 8x to the 5th, that would be 3x to the 5th. Okay, now you might notice that we're working over z5, but we have some exponents here, like 11, that are much larger than 5. And I want you to remember that it's only the coefficients that are living in this ring z5. The exponents on x, those are whole numbers. And so we don't want to take 11 and reduce it to 1 modulo 5 because those exponents are not living in z5. Okay, now it's natural to wonder if you have a base ring R that has certain properties, then what properties accrue to the polynomial ring R adjoin X? So here's an example of such a thing. So theorem 4.2 in your book says that if R is an integral domain and we take two polynomials in the corresponding polynomial ring, then the degree of the product polynomial is exactly equal to the degree of the first polynomial plus the degree of the second polynomial. And we can write down a proof for that in fairly short order. So we start off with two polynomials, f and g, as you see written there, where the leading, am and bn are the leading coefficients, and they're both non-zero. So if we go back to our list of terminology on a previous slide, that means that the degree of f is equal to m and the degree of g is equal to n. And now if you go ahead and multiply these two polynomials together, you see that we get a new leading term in the product, and that would be this one, with leading coefficient am times bn. And we know that that leading coefficient is non-zero because in an integral domain, if you take any two non-zero objects and multiply them together, the product must also be non-zero. Therefore, the degree of the product of the two polynomials, f times g, is m plus n, and that's the degree of f plus the degree of g. Now, as a corollary to this theorem, we find that if R is an integral domain, then the corresponding polynomial ring R adjoin X is also an integral domain. And here we remember that in order to be an integral domain, a ring has to have an identity, it has to be commutative, and it has to have no zero divisors. So we already saw in previous slides that if R is commutative, then the corresponding polynomial ring is also commutative. If R has identity, then the corresponding polynomial ring also has identity. And so the only question here is whether the polynomial ring has zero divisors. Well, if you had two non-zero polynomials and you multiply them together, theorem 4.2 up here tells you that the product must have a degree, namely it's the degree of the first plus the degree of the second. So that means that the product can't be the zero polynomial because the zero polynomial does not have a degree. Hence, the product of any two non-zero polynomials in Rx will again be non-zero. Okay, we saw a moment ago that this polynomial ring, R adjoin X, is capable of being an integral domain, but it turns out that it is never a field. Even if the base ring, the ring of coefficients R, is a field, the corresponding ring of polynomials is not a field. To see that, you can take a look at the polynomial f of x equals x, and then ask yourself, that non-zero polynomial, does it have a multiplicative inverse? That is there another polynomial that you can multiply by x to get back to 1? And the answer is no. In fact, you can use Theorem 4.2 on the previous slide to prove that. In fact, that may be one of your homework exercises. All right, well, what that means for us is that division is going to be a problem in polynomial rings, just like it was in the integers. Now, it might be good for us to remember from the dim past a little bit about polynomial division. We're going to try and do that now. So we're going to take these two polynomials, x squared plus 1 and 2x plus 9. We're going to divide 2x plus 9 into x squared plus 1, where we are regarding these polynomials as having rational coefficients. Well, how do we do that? So here's 2x plus 9. My divisor going into my dividend, x squared plus 0x plus 1. And I look at my leading term of my divisor, which is 2x, and I ask how many times it goes into my leading term of the dividend, which is x squared, and it should go in 1/2 x times, right? If I take 1/2 x times 2x, I get x squared right on the nose. And then if I take 1/2 x times 9, I get 9/2 x. And then you might remember that the next step is just to subtract. So the x's go away. I get 0x minus 9/2 x, which is just minus 9/2 x. I drop down the 1. And now I do the same thing all over again. I look at the leading term of my divisor, which is 2x, and I ask myself how many times it goes into this new leading term. And it turns out it goes in minus 9/4 times. Because if I take minus 9/4 times 2x, I get a minus 9/2 x. And then minus 9/4 times plus 9 is a minus 81/4. And then again, we subtract all of this stuff. And what we get down here at the bottom is 85/4. And now we can no longer divide our leading term of our divisor, 2x, into 85/4. And so what we see, if we write this out, is that the quotient is 1/2 x minus 9/4, and the remainder is 85/4. So we could write that like this. We could have x squared plus 1 is equal to 2x plus 9, which is our divisor, times our quotient, which is 1/2 x minus 9/4. And then plus our remainder, which is 85/4. All right, now what I want you to imagine is, let's suppose we tried to perform this very same computation over the integers instead of the rational numbers. Well, we would have trouble right from the outset because there would be no coefficient that I could put on x in order to make that coefficient times 2 here equal to 1 there. And so very much we're using the fact that the rational numbers are a field, right? We have an equation of the form ax equals b that we need to solve in order to go through this computation that we can solve when we're in a field always, but when we're not in a field, like we're in the, say we're in the integers, we can't solve this. So this computation breaks down if we're attempting to perform it over the integers as opposed to the rational numbers. It can be interesting to perform this very same computation in other polynomial rings. But as we saw on the previous slide, we probably want to make sure that our coefficient ring is a field. And here our coefficient ring is Z11. 11 is prime, and therefore Z11 is a field. Why don't we try it and see what happens? Here we're taking, again, 2x plus 9, and we're dividing it into x squared plus 0x plus 1. Now I ask myself, okay, I'm taking the leading term of my divisor and trying to divide it into the leading term of my dividend. So I want to know, what is it that I multiply by 2x in order to get x squared? And I submit to you that it's 6x. Now why should that be the case? Well, x times x is x squared for sure. But remember, if we take 6 times 2, we get 12. But 12 is really 1 in Z11. Okay. And now we take 6x times 9, which is 54x. But 54 is really 10 in Z11. And what do we do then? Well, we subtract. X squared minus x squared is 0. 0x minus 10x is a minus 10x. But remember, minus 10 is the same as 1 in Z11. And now we drop down to 1. And then we do all this stuff over again. I want to take the leading term of my divisor and divide it into the leading term of this new object, which is x. So I ask myself, what is it that I multiply by 2x to get x? And again, 6 is going to be involved. If I take 6 times 2x, I'll get 12x. But remember, 12 is really 1. So I just get an x there, and then 6 times 9 is 54, which again is 10. And we subtract here, and x minus x is 0. 1 minus 10 would be minus 9, but minus 9 is really 2 in Z11. And therefore, when we write all this stuff out, we see that x squared plus 1 is 2x plus 9 times the quotient 6x plus 6. And then we have to add on this remainder term, which is 2. So you might remember that when you're doing this division, you want your remainder to ultimately be something that has a degree that's less than the divisor. So here our divisor has degree 1, and our remainder, sure enough, is a constant with degree 0. Now sometimes the remainder could have no degree. In fact, if 2x divided evenly into x squared plus 1, then the remainder would be 0. And remember, the 0 polynomial does not have a degree. Okay, the upshot of all of this is that when f is a field, there is a division algorithm on the polynomial ring f adjoin x, meaning that if someone drives up and hands you polynomials f and g, where g is not the 0 polynomial, then you can find quotient and remainder polynomials in f adjoin x, where little f is equal to g times q plus r, where either r is equal to the 0 polynomial, which means that g has divided into f absolutely evenly, or at the very worst, the degree of r is strictly less than the degree of the divisor polynomial g of x. Okay, the proof is rather tedious, but it is interesting, and it involves induction on the degree of f. I think you should read this proof. It's theorem 4.6 in your book. And at the very least, you should go through and see where it is needed that the base ring R, the ring of coefficients, where we need that ring to be a field. That would be a good thing for you to do, is to go see where that hypothesis is used.